So today we want to talk about inverse matrices. Before we can talk about inverse matrices, we have to define what the identity matrix is. So the identity matrix is the matrix when you would have ones along the main diagonal and zeros everywhere else. This is called the identity matrix of size n, and sometimes you'll see that as I sub n. The sub n just tells you what dimensions you have. So I2 is a 2 by 2, I3 means a 3 by 3 identity, and I4 means a 4 by 4 identity, and that could continue up to any dimension. The deal with the identity matrix is that you can multiply it on either side of a square matrix and get that original matrix back. And we know that in general, multiplication is not commutative. So in general, when you multiply on one side, you don't get the same thing as when you multiply on the other side. You can in rare instances, but it's not a rule that has to work that way. But if you have an identity matrix, it is commutative, meaning I can multiply on either side that I want. And not only that, but when we do that, we get back something specific, which is we get back the original matrix. So it's basically the identity matrix is the matrix form of 1, right? Because if I were to take the number 1 and do 5 times 1, I would get the original number 5 back. And if I did 1 times 5, I would get the original number back. So the identity is the matrix form of the number 1. So let's see that in action. It says find AI and IA given this A 3 by 3 matrix. So the claim is that we can multiply first A by the I and second the I by the A, and either way we do that, we'll get the original A matrix back. So let's just see how that works. First of all, it's a 3 by 3 and another 3 by 3. So we are allowed to do this multiplication. The inner numbers match, and it also tells us that we will get a 3 by 3 answer. Drawing some kind of dashed lines in here to help us with this multiplication will look like this. And remember, we're going to go across and down, across and down, across and down. I'm going to do this fairly quickly, but if you take 1 times 1 plus 5 times 0 plus negative 2 times 0, you get 1. If you take then, keep going down this first column, if you take 3 times 1 plus 3 times negative 1, plus negative 1 times 0 plus 6 times 0, you'll get 3. And this bottom row, 0 times 1 plus 1 times 0 plus 4 times 0 gives us 0. And we have now finished this first row. Repeat with the second row. 1 times 0 times 5 times 1 times negative 2 times 0 is 5. 3 times 0 plus negative 1 times 1 plus 6 times 0 is negative 1. 0 times 0 plus 1 times 1 plus 4 times 0 is 1. And that very last row then, if we take 1 times 0 times 5 times 0 times negative 2 times 1, we get only the negative 2. And so on and so forth. And I'm going to just go ahead and fill these last two entries in. I think you'll believe me at this point, we're going to get that original matrix back. So I challenge you to do this next one on your own. It is going to work. If you multiply across and down, what you're going to find is that you get that same original matrix back. It's kind of uninteresting, really, once you get into it. Maybe at first the claim is a little bit unbelievable, but after you start doing it, what you can see is because you only have the single 1 in any column, you only get that 1 entry back every time. So every entry you just get back itself. So this is a really important matrix. We're going to use the identity matrix to do a lot of other things, and we're going to use that to find inverse matrices. The next thing we want to talk about is how a system of equations can be written in what we call compact form using matrices. We call this a matrix equation. So we've written this in one way before, kind of a review. We've written this as what we call an augmented matrix. Where we put the vertical line as the equal signs, and then we just do coefficients. So we've done that before. This is a different way to take a system of equations and write them with matrices. In this, we're going to write it as the form AX equals B. Okay, so these would be our different matrices. So A is the coefficient matrix with all the coefficients that were on like the left-hand side. The matrix X, capital X, are the variables, X, Y, and Z in this case. And then our final matrix B are the constants that are on the other side. So this says multiply A and X above to show that this system of equations really works. Like, do you believe me that we can write this system of equations like this? Well, let's try it. So if I take A and I just write down these coefficients, and I multiply that by X, the variables, what do we get? Okay, so if I'm multiplying across and down, notice that I would get get a different color, 1x plus negative 2y plus 3z. I would get negative 2, sorry, let me go back, I would get 1x minus 2y plus 3z, and we know what that equals. We know that particular equation equals negative 1. Let me pick a different color. If I do my next row, I'll get 3, that is not a very different color. Let me try again. I would get 3x plus 4y plus negative 2z. And what is that equal to? That's equal to 1. And for our last entry, we would get 2x minus 3y plus 7z, and that equals 6. So yes, we can write it in this way. Basically what happens is we end up not writing this. We don't write this intermediate part. We just write the other parts. So we do A, the matrix A, times matrix X, equaling matrix B.